The title of this video is Poisson distribution as limiting form of binomial distribution. The meaning is under certain conditions, binomial distribution becomes Poisson distribution. So first we see what are all the conditions. First, we recap the binomial distribution is notation symbolically represented as b of n comma p, where n is the number of trials and b is p, small p is the probability of success probability. These two quantities are most important, and NP is mean for binomial distribution. Here, the condition number one is n tends to infinity, that is, n is indefinitely large, and small p is very small, p tends to 0 and n tends to infinity are most important conditions. And NP means rate of success is finite, and this will be denoted as lambda. So P and Q are in terms of lambda and denoted and will be replaced in future. The total process actually contains, we are starting with binomial distributions probability mass function and apply the conditions. We will end at the Poisson distributions probability mass function. So we know P of x equal to R for a binomial random variable x. It is NCR P power R Q power n minus R, where R is 0, 1, 2, 3, etc. up to n. Now NCR is n into n minus 1, n minus 2, etc. n minus R plus 1 by R factorial. And P power R, Q is 1 minus P whole power n minus R. Now each of this p, small p, is replaced by lambda by n. So the next step contains, instead of p, we have a lambda by n for both the terms. So after that we take lambda power r outside and r factorial also outside. So after taking lambda power r, the denominator n power r, each of the n is taken to each of the factor in the numerator and divide respectively. So we get lambda power r by r factorial into n by n, n minus 1 by n, etc. n minus r plus 1 by n into 1 minus lambda by n whole power n minus r. So if we divide each of the factor by n, the balance terms becomes 1, 1 minus 1 by n, 1 minus 2 by n, etc. up to 1 minus r minus 1 by n. So already we take lambda power r by r factorial out, and these terms after dividing by n, we are getting this r factors like this. The uh, ending term is 1 minus lambda by n whole power n minus r. Now in this expanded version, we are going to apply limit n tends to infinity on both sides. So left side is p of x equal to r limit n tends to infinity. The right side, we are going to apply this n tends to infinity, uh, and this the first term lambda power r by r factorial has no n, so we can take that term out. Lambda power r by r factorial is independent of n, so it will not be affected by the limit application, so we are taking that term out. Balance terms, each of that term contains n, so applying separately, and 1 minus lambda power by n whole per n minus r is splitted as power n and power minus r. So separately applying the limits, the first square bracket terms gives 1 because 1 by n when n tends to infinity becomes 0, and each of the factor is 1 minus of 0. So finally we get 1 for that term. Limit 1 minus lambda by n whole power minus r also, in the same sense, we get 1. The last term limit n tends to infinity 1 minus lambda by n whole power n is simply e per minus lambda. Finally, we get e per minus lambda power r by r factorial. That is, when applying the conditions n tends to infinity, p tends to 0, and np is finite, binomial distribution becomes Poisson distribution. That means Poisson distribution is a limiting case of binomial distribution.